Good morning, everyone. Today, my name is Zhi Wang from University of Houston. So today, I'm going to present an automated formation top labeling and well depth matching by machine learning. So under the current digital system, the training data and parameters are integrated, processed, and transferred by these digital advisory systems. And the visualization of the training parameters and the intelligent analysis process are some key components in this system. So during this process, depth matching plays an important role because in order to get an accurate formation interpretation and a precise training control, the depth of the monitored data from multiple wells need to be synchronized before the evaluation. Just by matching the patterns from the different wells from the same field, we can have a better understanding of the formation information in that field. So as a function of depth, there are a lot of measurements can be used to support the depth matching formation interpretation. Just by probing the physical properties around the borehole, we can get the rock conductivities, radioactivities, the porosity, and the permeability, etc. So among these, gamma ray log is widely used for depth matching or correlation, since it is a good indicator of the natural radioactivity. And nowadays, it is standardized as a basic measurement. So a distinct pattern on the gamma ray log is oftentimes presented when there is a disrupt change of the formation properties or the rock types. So the traditional practice of depth matching is usually accomplished manually by picking the similar sequential patterns across different gamma ray log curves. However, this is labor-intensive, and it always there lacks some consistent evaluation criteria. And there are other methods based on some distance or similarity matrix to do this. However, they are prone to some distortions or shiftings in the logs, and sometimes it needs a lot of human intervention. So in our work, we proposed here we present some conventional methods to do this. Cross-correlation is one of the conventional methods can be applied to align two patterns of two time series. However, when there exist large distortions or shiftings, the accuracy of this method can be very low. And another method is dynamic time warping, which can be a possible method to do depth matching to match the two time series. But it is very time consuming as the length of the time series increases, and it often needs a lot of human intervention because to do depth matching by dynamic time warping, we need to align the both ends of the time series. So in our work, we proposed a machine learning-based method to do this. So when we are given two gamma ray logs, the question is, can we just simply linearly align them, align every point on them? The answer is no, because oftentimes the length of the gamma ray logs is too large, and there exists a lot of large shifting and distortions in them. So just simply linearly matching them will cause a lot of problems. So usually to do depth matching by machine learning, we can split it into two steps. So the first step is that we can propose some labeled or unlabeled patterns on one of the gamma ray logs, and then we align them on the other logs. By doing this, these long gamma logs pairs can be cut into a lot of smaller segment pairs, and they are both aligned at the both end. And the second step is we can now perform the linearly or non-linearly depth matching strategies on these smaller, shorter segments. The idea behind this is that usually the more proposed patterns are aligned on the gamma logs, the shorter the segment will be, so the more reasonable it is to adopt a linear or nonlinear matching strategy. So now the work of the depth matching the main work of the depth matching will be to align these patterns on different gamma logs. Several works have been proposed to do this first step, which is to align patterns on the gamma logs. And they either use a sliding window to do exhaustive search on the logs, or they just simply predict the position of the wanted pattern on the logs. So, however, there still exist some problems. For example, the multiple matches and the low recall problems. In our work, we proposed a dynamic matching process to do this first step by using a deep convolutional neural network. So now, when we are given the segment of a gamma series, which we call a query, and that it indicates a proposed pattern on the reference log, our objective is to find its matched pattern on another log, which we call the target log. In our work, we propose the tracker. It is a sliding window which can move back and forth on the target log until it finds the matched pattern on that log. And this process is directed by a deep neural network which implements multitask learning that predict an action and the matching probability at each movement to guide the tracker. So the workflow of this process can be split into 3 parts. Firstly, we need to propose a pattern on the reference log. At the same time, we take the position of this query as the initial position of the tracker to initialize the tracker. And then we start these moving iterations. At each iteration, the model will predict an action vector, which indicates the probabilities for each movement, which is moving forward, moving backward, or stop on the target log. And a stochastic action decision scheme is performed on this vector to choose an action for the tracker to move on the target log. And then, at the same time, we check the matching probability to see if the pattern has been matched at the current location. So this matching process doesn't need to search for the whole target log, which is unlike the exhaustive search. And also, it doesn't need any pre-assumption about the matched pattern. And the multitask learning method can leverage the query and its initial position and the prior local information. And meanwhile, it takes a global view of the target log to guide the tracker's movement. So our process is fully automated, and it doesn't need any human intervention. So here we show the detail of the action decision scheme. Occasionally, there might be a lot of mispredictions for the actions during this moving process. And those mispredictions can stall this moving process before the tracker moves to the matched pattern. And so in our work, we use 2 steps of post-processing to fully eliminate these mispredictions. As can be seen, the first step is that This green line indicates the decision of the actions. The upper line indicates that we need to move backward, and the lower line indicates that we need to move forward. And this red dot means the ground truth. So as can be seen, there are a lot of mismatches during this process. Firstly, at each positions of the trackers, we sample its adjacent positions to form a mini-batch input. And by average this output of this input, we get intermediate action vector. And then we average the historical intermediate vector to get the final probability distribution for the action. And then the direction of the action is stochastically chosen based on these probabilities. And the step size of the action is the probability of the chosen direction and times the default step size we set. The input of our model is a dual channel input, and the first channel is the whole target log, and the second channel is a replicate of the first channel except for subsequence replaced by the query. And we train our model based on 177 synthetic gamma log pairs, and they are generated from 59 real logs. And we sample more than 1 million training samples extracted from these log pairs. And we use learnable weights to balance these losses during training. So the accuracy on the training and validation data set are both 98% or above, which indicates that the model effectively recognizes the patterns and captures the spatial correlations of them. And on testing data, we have 91% or above accuracy for the action vector or the matching probabilities. And the confusion matrix shows that we have both high precision and high recall. So here we show the effectiveness of the stochastic action decision. So by 2 steps of the post-processing, the mispredictions are fully eliminated. So here we show the result of this matching process. As I have said, the tracker will move back and forth on the target log. And at each iteration, we check the matching probability to see if the pattern has been matched or not. And if yes, we stop this process. And if not, we continue this process until the maximum iterations. And for those who doesn't match anything, in the end, we just simply discard them. So by adopting our model to do the first step, as can be seen, the whole target log and the reference log is cut into a lot of small segment pairs, which are aligned at the both end. And for these matched pairs, we can then perform a linear or nonlinear matching strategy to match every point of them to get the final result. So now to conclude, we propose an automated gamma ray log pattern alignment and depth matching algorithm using deep neural network and multitask learning. So a dynamic matching strategy is stochastically drafted to shape the tracking window until it finds the best matched pattern in the target log. And our experiment result shows the effectiveness of this model, and future work will be based on improving the adaptiveness of the model on various data. And that's all. Thank you.
To our speaker, we have time for one question here.
Thank you very much. Very interesting work. I want to ask you if you would like to tell us something about how you decide what is the size of the matching window that you are sliding, and also what do you do to avoid, because as I understand, you said that your algorithm looks globally. However, as I understand, it should be having something like a stopping criteria when you have a very very high probability of matching. So you're not going to examine the whole signal, right? You're starting from your initial location,
Yep.
and then you move until you find a location that seems to be matching. But the matching is not going to be 100% necessarily, right? So is there a stopping criteria that you determine there?
So,
Sliding window size, one thing, and if there is a stopping criteria, yes, thank you.
so the sliding window size can be changed. In our work, we used a fixed sliding window, and based on the how large your proposed pattern is, and for the second question, which is how we stop this process, we use multitask learning, which will predict an action for the tracker. And at the same time, I said I have another prediction, which is the matching probability. And for each iteration, we check the matching probability. And this probability, if it's higher than the threshold, we think it matched, and we stop this process.